There you go. All right, guys. So with that, what we are going to do today is the last stop in the topics of optics, and we're going to look at the combination of lenses. Okay, so what happens when you have more than one lens, or I mean, in reality, you can have a combination of lenses and mirrors if you like. But I think in comparison to what you use every day, relative between mirrors and lenses, I think you use lenses more. At least it's stuck in your eyes. Your eyeballs here contain lenses, right? That's how you focus the light, the images, and everything around you toward your retina. So at least that lens system is already in your eyes. And camera that you use, the projector that you might see in the classrooms, and what else? Like, I mean, it's everything pretty much, like pretty much lenses, because usually you have transparent medium that do the job. Okay, so we are going to just look at just the combination of lenses. Even though now you understand that if you have combinations of mirrors, the concepts stay the same, but it's just application is just way smaller. So let's take a look at lenses. And what we have in front of you right here is now you have two lenses system, lens 1 and lens 2. They have different focal length, and then you have an object. Now just, okay, look at this object a little bit. It's just a pencil. That's the tip. It's actually pointing, well, it's pointing down. So think of it like you have your pencil and you just have the tip of the pencil which is pointing on the table or something like that. Yeah. And the eraser type, I mean, the end of the pencil is on the top. That's kind of like counterintuitive a little bit, but that's what it is. Okay. So what you have an object in the front of lens number 1. So that's on the left side of the lens 1. And then the question is still the same. What is the final image that you get out of this two lenses system? Okay. And what's the type of the image? Is it real or virtual? Is it upright or inverted? What is going to be the magnification? And where are the location of the final images? That's it. Okay. So those are the 4 questions that, I mean, if you can answer all these 4 questions, that's it. You solve everything. Sounds like a good plan here. Okay, so how can we do this? First thing first, I think this is the easiest, and I think this is the one that you can sort of like think in your head yourself. The final magnification can be found by taking the magnification of each lens. Does that make sense? So in this case, you have 2 lenses. So that means if lens 1 is magnifying with the M1 magnification, and if M2 is the lens number 2 that do the magnification. So the total or your final image should have the net magnification of the product between M1 and M2. Does that make sense? All right. So that means if you have even more, you have like, 12 lens system and all this stuff, then of course you just take M1, M2, M3, all the way to M12 and then multiply them all. You're going to get the final image magnification. Okay. So that's done. So this is the easy extension from the equation of magnification. So this one is down. Now, the steps that we're going to take is very simple. What you will do is just think about, okay, the object is right here. So let me highlight that one. It's like super, super small here. There you go. Let me highlight that. That's the yellow one. So that's the pencil. It's the real pencil with the tip down. It's being placed in front of the lens number 1. So you just apply the lens equation and try to figure out the image location of this object due to lens 1. Does that make sense? So once you apply that one, you have a location of the image, you have the type of the image, and everything is done. Then all you need to do for the lens number 2 is just you take this image from the lens 1, treat it as an object for lens 2. Is that cool? So that means you just recalculate your position of your object again, which is the image from the first lens. So this is going to be your location of the objects for the lens 2. And then you redo the whole process one more time. So now you have an object here, you have lens number 2 there, and then you figure out the final image. Your final image will just show up, and it's going to be the big dude over here. And that's it. That is your final image from the 2 lens system. See? So if in the future you have more than this, okay, no problem. You just take the image from lens 2, treat it as an object for lens 3, and then you do the calculation one more time, get the image. And if you have 4 lens and then you take the image from the 3rd lens, treat it as the object for the 4th lens, and then you do the calculation all over again, on and on and on. So this process just keep continuing. Cool.
ไม่ต่างอะไรจาก
All
การ
right.
ไม่เข้าหรอก
And this is where
เข้า
the
เพื่อให้สบายใจ
negative
เฉย
object distance might happen. You guys see this? Because look at this
ๆ
one.
นี่นะ
If
อา
by
จารย์
if,
ก็ฟัง
by
เกาหลีเนาะ
accident or whatever, if your
เปลี่ยนเป็น
lens
อะไร
number 2 turns out to be, let's say right here, and let's say the image from the first lens just shows up behind. When I say behind, in this case, left
ไอ้
means
นอน
in
อย่าง
front,
นี้เมื่อคืน
right
ไอ้นอนอย่าง
means
นี้เมื่อคืน
behind. So in this case, it
แล้ว
means
ก็แบบ
the
โอ้ย
object for the second lens
แบมสวย
appear on the back side.
ว่าไงแบม
Oh, I can
อะไรนะ
help with that. Why I don't hear anything? That's weird. Oh, my bad. But you guys still hearing me though, right? Wait, give me a second here. Oh, I think I might forgot to put the whoa speaker. Okay, it's just sound system there. Got it. Okay, all right. That's why I don't hear anything. It's just quiet on my side. Okay, guys. So I think it's good. All right. So what you have over here is there is a chance now that the location of the object for the second lens appear behind the lens. Oh, yeah. And that's when you're going to get a negative. Here, let me put P. P is our object distance. So that could have a case that the object distance turns negative. That's what it is. Okay, so that's why just want to confirm my statement one more time that we said that if you have only single lens, your object is always on the positive side because you take that as your object distance. So you're never going to get negative object distance when you have only single lens. Does that make sense? All right, and this might be the case. However, from the look of it, because they already draw the figure so nicely, so from this particular setup over here, the image from the first lens still shows up in front of the second lens. So the object distance for the second lens stay positive here. So this is fine. Okay, now let's dive in, guys. How can we do the full calculation over here? So I have this full question shows up on the last slide of this handout over here. 2 lens, it's supposed to be 2 lenses, I guess, separated by a distance of lenses, yeah, by a distance of 40 centimeter are used in combination. The focal length F1 is given, F2 is given, and you guys know because these 2 are converging lens, is a convex lens. So what you can put actually just to make sure that you won't make any mistake here, just put positive sign in there. Okay, an object 4 centimeter high is placed 15 centimeter in front of the first lens. So that's where the P1 has already been given here to be 15 centimeter. So I can put there P1 there. In front of the first lens, find the intermediate and final image distances, the total transverse magnification. They put the transverse just to emphasize that you guys doing everything in one dimension. So the size of the object mean is just the height. Yeah, the transverse is just the height. And the height of the final image should be. Okay, cool. Let's go for it, guys. So let me do the color coded here. I'm going to treat calculation on lens 1 using the blue ink here. So let's take P1 as the problems already gave you 15 centimeter. That's your object distance. Okay. And followed by the focal length of the first lens is given to be 10 centimeter with the positive sign there. Cool. So from here, you will be able to figure out the Q1. So you do 1 over Q1, that's your image distance from the first lens is going to be 1 over F1 minus 1 over P1. And then it's going to be 1 over 10, which is positive, minus 1 over 15. And I'll work out the number a little bit. It's going to be 5 over 150. Is that right? So it's going to be 1 over 30. So your Q1 is 30 centimeter. That's it, guys.
Okay.
Okay, is my math correct? I hope so. Just like don't have any confidence like adding, subtracting numbers here. Okay, that's it. So that's your image location that you got from lens 1. Cool. So far so good. Now, if you look here, and if you try to draw things sort of like, in scale here, so this is 10 right there, P1. So your P2, it's going to be triple that distance, and that's P2 right there. Okay, I'm sorry, Q1, sorry, my bad. Sorry. That's what's a P1 there. So your Q1, your image location is going to be triple of that P1. So that where your Q1 is right there. There, let me mark on blue there. Okay, that's 30. Now, let's move on to the next lens. So I'm going to use the green color here for the second lens calculation here. Now, because your image from the first lens is 30 centimeter away from the lens 1. However, lens 1 and lens 2 are separated by 40 centimeter difference. So that means you still have 10 centimeter left here for P2. You guys with me? Okay, all right. Now, because your image still shows up on the left of the lens number 2, so you can still treat this one as an object for the lens number 2, and it still have a positive sign of the object distance because it's still on the left. It's still in the front. Cool. So with that, I'll start doing the second part calculation here. P2 is positive 10. F2 is already given to be positive 12 centimeter. And now you can figure out the Q2, your image location for the second lens. Is going to be 1 over F1 minus 1 over P2, sorry, 1 over F2 minus 1 over P2, and it's going to be 1 over plus 12, subtracting 1 over 10. All right, and that gives you now negative 2 over 120, and that is negative 1 over 60. So that means your Q2 is negative 60, guys. Whoa.
Okay.
All right, this is good. When you say negative 60, what does it mean? It means your final image location will show up on the front side. Remember the front side of the lens, that's where the light shouldn't be. So when the light shouldn't be, your image shouldn't be there. I mean, it shouldn't be real. And that means you're going to get the location in the front of the lens. And let me write it in red here. That's your distance that you got. That's your Q2 right there. That's 60 centimeter. Does that make sense? Not bad. Now, the point that you have to calculate next is, Ajahn, so what is the final image? Sort of like, what is the final image type? What's the classification of your final image? Is that going to be real, virtual, upright, inverted? What is the magnification? So what we can do next is this. Because at the end, your image has a negative sign. We already agreed on this. Definitely, you're going to have a virtual image because that's where the light shouldn't be. It's impossible for you to have the negative, a negative image location. So you can conclude that now you have a final virtual image. Cool. That part is done.
Okay.
Now, the second part is it upright or is it inverted? So what you can do next is, let me add on top of this one, we have second equation to deal with, the magnification equation. Yeah? Yep. Any question here? Okay, no. That will be the first time somebody open up the mic and ask question. That would be nice. Okay. However, they already had that like after class. Okay. But anyway, so over here, I can put the subscript one there just to see, hey, what is the what is the magnification of from that you get from the first lens? So it's going to be just, don't forget, we take the negative sign along, Q1 over P1, and you just substitute the numbers that you have already calculated. So the Q1 is 30, so negative sign is still there. 30 over P1 is 15, so that is negative 2. Just leave it there. But at least you know from the final result that you get from M1 that is negative. So what it says is the first image that you get from the first lens is going to be upside down, and it's going to have magnification of 2. You guys with me? So that means if you look at just the first lens alone, let me do the blue color here. So this is your object right there. Your image due to the first lens alone will have this result. It's upside down and it's twice as big. Cool.
Okay.
All right, but that's not ends of the story just yet. We have another magnification to do. So you move on to the M2 down here, and let me follow up here. M2 is going to be negative Q2 over P2. So you do the same magnification for the lens number 2. Negative sign is there. Q2, it's negative 60. So let's take the negative sign along. And P2, that's 10 centimeter there. So you get positive 6 from the M2. Cool. So that means what I'm saying, what I'm seeing over here is, if you just look at the lens 2 alone, the M2 has a positive final result. So this means it's still upright, and it's going to be 6 times the size of the object for the lens 2. You guys with me? So look at this one. What happened here? This is the object for lens 2. It's right here, waiting here. And the final image for this is still upright. Upright means it's oriented in the same direction. So see, the final image stay in the same direction there. And it's 6 times larger. Cool? All right. But in reality, you don't have to, follow the whole fine detail of what happened on the first lens, what happened on the second lens, because you can just jump right into the final image like this. Your final total magnification is going to be M1 times M2. M1 is negative 2, just plug it in there. M2 is plus 6, just put it there. Your final result for the total magnification is negative 12. Oh,
Okay.
is that cool? When I say cool, what does it mean? It means you can just interpret your final result right away. But you get the total magnification and everything to be negative. So it means the final image from these 2 lenses is going to be inverted. Got that one?
Okay.
See that? You start here. The final image is inverted, and it's going to be 12 times as big as the original height of the object. And you are done.
Okay.
Conclusion, your final image is virtual, shows up at negative 60 from the second lens. So that means you can think of it like your final distance over here could be 20 centimeter if you like, okay? And it's going to be inverted. Yeah, let me mark on here. Inverted. And 12 times as big. So you get 12x magnification and you are done.
Okay.
Cool. All right. So I hope this clear things up about what happens if you have multiple lenses system and then you still have to do the calculation. All you need to do is just do one calculation at a time. One lens calculation at a time, and then you just take the image from the previous lens to be the object for the next lens, and then you just keep doing it. And the magnification equations will allow you to find out what is going to be your final total magnification by take the product of all those M's, and you are done. Okay, interpretation stays exactly the same. And that's why I said every time that you grab the equation of the magnification, please grab that negative sign along.
Okay.
That's kind of nice, right? Because you can see that if you don't grab that one and you only talk about magnification, you still have question about, hey, is it upright, inverted, on and on. It's going to get crazy when you have multiple lens system like this. All right. But if you stick with the negative sign in the front, your interpretation at the end of the calculation is going to be straightforward. All right. Just read the results and you are done.
Okay.
All right, guys. Can you figure out what kind of device you are talking about here? You have 2 lenses. One lens close to the object. The other one is going to be closer to your eyes. So actually this system that you are looking at right here is just a microscope. Yeah, and that's how you set up your microscope. If you do like biology labs and all the stuff, you want to take a look at something. And then because of the focal length that's chosen here, you only get 12x. But if you take like, lens number 1 to be super, super duper small focal length, and then you take lens 2 to be, somewhere about okay. And then you can adjust until you might get like 60x or maybe even 100x microscope. Yeah. So that's what you have here. All right. And if you remember when you do like biology lab, Every time you put like a slide, you take a look at some, virus or bacteria or something. When you move your cover slide to the left, your image will travel to the right. If you move your cover slide up, then the image will go down. That's what it is. It's right here. Because what you're seeing is going to be inverted because that's what your final image is supposed to be. And as you can see, what you see is just you see by eyes, because what you're seeing is a virtual image. Okay, it's not a real image. So that's what it is. But you still might wondering about Ajahn, if it's a virtual image, you can only see by your eyes. How can you broadcast whatever the image that shows up in the microscope onto like big screen or whatever? Of course, they will have like a secondary system that redirect the light into some other thing that you can focus on the screen. So I mean, what you're seeing through your second lens, that's going to be virtual image. But in between, you might be able to redirect all those rays that coming out here. Sorry. Yeah. Right. The ray, even though it diverges, you can see this by eyes. Just place your eyes here and take a look at it. But then you can still redirect this one to other places and then do the focal onto some CCD camera. And then you connect to, the HD TV and all this stuff, on and on. All right. So the light is just diverging. Doesn't mean it's disappear. You can still play around with those diverging lights, make them converge again, and then you still sort of like get back the original information about the object. Yeah, and then you do that as the take a photo, put it on a film, put it on a CCD camera, put it on screen, on and on. All right, guys, and that concludes this chapter over here about waves, sounds, and lights. Is it good? All right. So I think you guys like this one because there's no calculus pretty much. Maybe there's only one or two about the oscillations. You only have to do differentiations. But once you're done with the simple harmonic oscillations, everything else pretty much like algebra and geometry. So you use a lot of sine, cosine, and angles, and the rest is just quite like number crunching problems pretty much. Okay, guys, any questions so far? All right, good. So I hope you learned something. And then just if you go back and read the text a little bit, they will have another system in comparison to the microscope. You might have a different setup using different low focal length of these two lenses. You can also do the telescope. Yeah, the one that you can, look at the stuff so far away. So it's just different selections of the focal lengths of those two lenses. All right, but this is so simple for you to see that you can now do the full calculation of this type of devices or instruments. Cool. All right, guys. So let's close this chapter down. Let's bring up the second or the third, actually. The last module will talk about electricity and magnetism. And then now that's it for this slide here. Okay, cool. All right, guys. So this is like a quick warning over here. Thing is going to get rough. Okay, this is not the right one. Sorry. So it's gonna be all right. For those of you that haven't downloaded it, you guys can download the new handout. I thought I put it last night. I totally forgot. I thought I did it already. It's on the Google Classroom already. You can download that one. And now we're going to move on to the charges, electric field, electric force, and Coulomb's law. That's what it's going to be a lot of fun.
Okay.
And just like a quick warning, and it's like a heads up here, guys, things going to get rough from now on. It's not that bad. It's just like saying that. So now you're going to get back to the, full steam mode that you're going to have to deal with the vector quantities again. Okay. So we have to deal with the vector summation, the vector products. You're going to do like the dot product, the cross product, plus calculus is back by popular demands. you guys probably missed it already. So we're going to have to deal with the calculus one more time. And here comes the bad things that I sort of put at the end. If you're going to combine them all, you're going to have to deal with the vector and calculus at the same time. So this is going to be your chance to take a look at the vector calculus, guys.
Okay.
All right, you'll have a chance. But don't worry, I'm not gonna, torture you guys with like super complicated question or anything. But I hope you will have a chance to take a look and see what kind of like things that we can do using vector calculus and treat electric and magnetic fields. Yeah, it will be a lot of fun, I think. All right, guys. So first thing first, how familiar are you guys with the electric fields? And of course, our sort of like big player over here is this dude here, guys, charges. This is the weirdness of our universe here. All right, we already had mass, and from the mass, you already got your gravitational laws, like Gmm over r square. You have the interactions between masses. You have gravitational pulls and everything. Those are the stories about mass, right? But it turns out our universe has something else for you. And that is charges. That is another side of the story that can also do some interacting stuff. You can still exerting the force. You can still have the pull, the push, and all the stuff coming from other things than just masses. And that is the charge. Okay, so the beauty of this one is the formula that you're going to use here still look as beautiful as the one that you use with the mass. And that's sort of like made physicists, like, back in the, a couple hundred years ago, dreams of having like a grand unifying theory in physics. It's just like, okay, they hope that they might have like a single equations that pretty much govern everything in physics. That's what they hope, because one clue of that stem from this. And you will see that the law that we're going to study, which is, there's a name, is a Coulomb's law, has the same forms as the one that you learned from gravitational laws. So it's like the same, shape of the equations, it's the relationship and everything. It looks pretty much the same. So that was the hope, all right? But we're not done yet, right? We haven't found the grand unified theory yet. So that's work in progress here. Okay, guys, so that's what it is. The law of the electricity and magnetism, of course, is going to play a central role in everything. The reason is because back at like, super down into the finest components of our universe, which is atoms, you have nucleus and you have electrons sort of like orbiting around. Okay. And you probably have learned so many times that the nucleus has a positive charge. That's where the charge comes in. And the electron has negative charge. And because this is a building blocks for everything else, you have like elements, you have compounds, material, you have molecules, you have everything. So you can say that you cannot avoid electricity and magnetism. And then you cannot avoid charges. It's because it's already built into our elements. The periodic tables just fill with charged particles. So it's right here, okay? So this is why we have to study this. What are those properties of charges? So what we have here. Now, so when you take a look at this one, first thing first, charges are different from mass in the first thing right away that you have to keep in mind. There are two types. In the mass, you only have single type, which is mass. And they can only do the attractive force. The mass can only do the attractive force. But now when you do the charge have two types. So physicists just assign something to it. They're gonna call one positive and the other one negative. The reason that they have to assign this because charges can either push or pull. So there are two directions of charge interactions that can happen, right? Not only attractive force anymore, you can have a repulsive force along with it. It depends on the types of charge you are dealing with. Okay, that's one thing you have to keep in mind. Now you have two ways of the interactions that's possible. Second is, all right, when you have the mass, you have 1 unit of mass using is a kilogram, right, in SI system. So we're going to have to assign something about that as well. So the amount or the quantity of charge, okay, the one that we name charge, it has a unit as well. And that unit, we're going to call it Coulomb. Okay, so you can sort of like make the quick analogy of the Coulomb to be what the kilogram is for the mass. So the Coulomb is the amount of charge that you get in your system. Cool. All right. So this one is comparable to the kilogram. So what you have here is Coulomb, the C right there. All right. Now, another fascinating thing about this one, and it's, I mean, the fascinating stuff never ends here in physics here. It turns out the complication is in here. You cannot pick any charge in this universe. When I'm saying this, it means it turns out electrons possess the smallest amount of charge in this universe. Isn't that cool?
Okay.
I don't know you have noticed this before or not, but electrons, it's like, it's big dude here. It's like it's doing all the tiny works around universe here. It's like, you know, on our earth here, electron is like, you know, we owe so much for electrons here. Electrons has charge built in, and I think everyone probably have seen this number before. It's about 1.6 times 10 to the negative 19th Coulomb. So every electrons will come with this amount of charge. All of those electrons, right, they're all the same, right? No matter which electron you're talking about, they will have this exact same charge. And it turns out to be the smallest amount of charge that you can get in this universe. What does it mean? I'm saying in this universe, you cannot find a particle with 1.7 times 10 to the negative 19 Coulomb charge. That's not possible.
No.
Seriously. Okay. So that means all the charges of any object or whatever has to be multiple of this E. Okay. Don't worry about, for those of you that probably heard about the fractional charges in, you know, quark system or whatever, that's not the business that we are going to deal with. But for regular stuff, objects around you, the amount of charge has to be multiple of this number. So you are already looking at something of here. Let me throw this word for you guys, even though we're not going to do anything with it. Quantized. The amount of charge is not a continuous parameter or continuous quantity. It's a jumpy quantity. It's multiple of electronic charge. Isn't that amazing? Right? So it's not like a smooth continuous value. It has to be. However, to your eyes or to our everyday experience, it doesn't matter, guys. It's down to the negative 19. So your eyes, you probably cannot see by your eyes, but I mean, for our everyday life, it looks smooth enough, because I don't think you can imagine anything can have that number, 10 to the negative 19. It's not even nano. Nano is negative 9. It's not even what else from the nano. When you go down to the nano, you can go to like maybe pico, you can do to femto, it's still negative 15. So when you deal with a number down to the negative 19, that's, oh, you cannot imagine, right? So that's why don't worry too much about the discreteness of the charge quantity here, right? But at least this is good to know, okay? All right, guys. So the unit of the charge is Coulomb. Think in your head, it works just like kilogram with the mass. All right, next. Now, what happened to the interaction between them? Now, when we have positive and negative, right, because you have two types of charges. Now, when are they going to attract? When are they going to repulse? Okay, it turns out it's easy. If you have the same types of charge, they're going to repel each other. And if you have opposite types of charge, they're going to attract. That's it. That's how simple things are. So what you have over here is, for example, if you have glass, that's somehow you charge the glass. When they say charge the glass, it means you have some leftover charge on the glass, like this. It's like you have like too much positive charge on it. Or you can imagine in the opposite sense, you lose some electrons out of glass. So when electrons just sort of like losing out, the net charge on the glass turn positive. Okay, because in general, you guys know when you hold up the pen, this is neutral. It just doesn't have any charge left on here, or there's any deficit or any surplus of charge. So this is neutral. So one way that you can make glass positive, so you either deposit some positive charge on it. It's kind of tough to do, right? Because Where can you find positive charge? It's not easy to find. So maybe the easiest way to do is just you just lose some electron out. Same thing. All right. So that these two give the same final effect of a glass having a positive net charge. And now if you have the pretty much another glass that also have the net positive charge, and then you place them nearby, they're going to repel each other. That's it. That's how simple things are. On the other hand, you might have something else like plastic. Plastic has ability to maybe, you know, draw in some electronic charge. So you have some electron deposits, surplus. You have some, you know, some leftover. So your net charge on the plastic is now negative. And when you have a net positive glass, then they're going to attract each other. Okay. So the conclusion about this one is when you have two kinds of charges, if you have opposite types of charge nearby, they're going to attract. If you have the same type of charge, they're going to repel. That's the whole thing. Now, when you look at, because now we know that electrons pretty much like responsible for things that, you know, can carry charge and all this stuff. So in terms of the material, you can classify the material to be three types, depends on how well the electron can travel or how well those things can allow charge to move inside. Does that make sense? All right. So that will be the first class. You say that you can call it a conductor. The conductor is the one that you allow the charge to move very easily. Like, of course, metal, silver, gold, copper, steel, seawater. Seawater is ionic. So you have like, you know, like sodium and chlorines, ion can travel, move around very easily. So those are conductors. In contrast with the conductors, you might have insulator, the one that the charge, cannot move very easily. Once you get there, it's stuck there. It cannot travel, so it won't do anything funny. Those are, for example, rubber, glass, oil, diamond, wood, and other stuff, right? You guys know this one doesn't conduct electricity well, okay? And this one is kind of like, okay, that's kind of common sense. You pretty much save using the rubber glove, for example. You can touch things without getting static charges and all that stuff. And of course, somewhere in between of the conductors and insulator, you have semiconductors. Okay, this is kind of weird in the sense that, all right, it's sort of, right, not a very good conductors in some way, but it's not like super good insulator. When I say not super good, not super bad, it means it somehow you can manipulate this because the property is just somewhere in between. So it allow you to switch between, wow, I want semiconductor to conduct now, or well, I don't want you to conduct, just, you know, pretend like you are insulator. So that's when you start to have something that is switchable. So you can have like, okay, I can have them move, oh, not move, move, and not move. And that's when you start to have some logic. And that's when the semiconductor business starts to creep in. So when you have this, you can create transistor that allow you to, you know, control the ability of the conductions of the electrons. Then you can say yes, no, no, yes, yes, no. Then you know, open the gate, close the gate, on and on. You have transistors. And then when you have transistor, then you build CPU, all the processors and everything. You get logics, you get everything down, and then you get computers at the end. All right. So enough for the introductions, I guess. All right. Here is the main business today. All right. I'm going to go slowly first for those of you that don't familiar with the electric field business at all. So if you take a look at the textbook usually will start with the electric force, and they try to force you to get to the Coulomb's law first. I don't know force or not, but it looks like they're going to start things with the electric force and introduce the Coulomb's law that's govern is the equation that allow you to calculate the amount of electric force, okay, among all those charges. But to me, it seems like force came from field, because we're going to use field to sort of, you know, understand how the electric force work, right? So it seems like it's redundant to study force and followed by the Coulomb's law and then come back and talk about electric field again. I don't know, it seems kind of weird. Doesn't make sense to me. So my logic is this: I am going to talk about electric field right away. Once you get the field, the force is like piece of cake.
Okay.
Seriously, because if you understand how the electric fields work, The force is just the consequence of having a charge in the field. You guys with me? Think about, I mean, the reason I would like to sort of like approach in this direction is because of this, guys. Remember, not, you don't have to remember this, but this is a mass. And everyone knows once they let it go, it's going to drop, right? Yeah. Why? Everyone understand this one easily because the mass is under the gravitational field. The gravitational field is pointing down. So imagine this. If I don't have the mouse here in our screen, on our screen here, you guys already know that there is a gravitational pull everything downward, even though there's nothing here. But you guys know in your imagination, let me say that. Your imagination say, Ajahn, there is something pulling down all the time. And once you place a mass there and you don't hold it, you just let it go, it's going to drop due to that gravitational pull. So I'm going to take the same approach. Why don't we use the same approach here? I am going to introduce to you guys the electric field, which is going to have the same experience as a gravitational field. Once you understand electric fields, force came from what? Just place a charge. Now you can imagine this one. Remember, charge is equivalent to mass. So now imagine this one, reimagine this to be a charge inside an electric field. So once I let it go, the charge has to travel. Cool?
Okay.
All right, so after the break, we'll start this process. So I'm going to show you how to think in terms of the electric field. Once we understand how to do the field, force will be a piece of cake. We'll see you after the break, guys.
Okay.
First. All right, so first thing that we're going to take a look at is electric field, okay? And the idea of the field is going to be exactly the same as when the mass has gravitational field. Does that make sense? So I think you guys sort of familiar with that kind of idea already. So imagine this. So let's look at this two figure over here. So what we are about to accomplish here is if you sit one charge right here. So let me highlight as the yellow, yeah, the Q. And let's say you have another charge, your second charge nearby. That's a Q naught over here. Okay. And then when they are close by, all right, let's take our focus onto this charge right here, the one that I highlighted red here, the Q naught. And let's assume that our Q, the positive Q over there on the left, is fixed in position. It cannot be moved. Okay, it's just there all the time. So the Q naught will experience a force. And because let's say that if the Q naught is also positive, you said when you have positive charge, they will exert the repulsive force, okay, among each other. So by having focused on the Q naught will experience a repulsive force vector F right there. Cool? Now you see this diagram over here and you understand how this goes, yeah? Okay, one more time. You have the Q, positive charge, fixed in place. This one is fixed in place. And then now you have the nearby charge Q naught. In the textbook, they usually refer to Q naught as a test charge. Test charge means just a charge that you can just, bring it around, bring along, or whatever you want to do with it. And then what you have over here is the force that will, the Q naught will experience a repulsive force showing in the blue vector F right there. That's a force. Now, I want to have you think in terms of the field. What will happen? So imagine just like what I talked about before the break. If you somehow don't have that at all, so you just erase this, forget about this one. Okay, don't worry about it. Just like, okay, let it go. Let it go. And you are looking at just this location alone at point P. Let me name this point P. At point P, even though now you don't have any Q naught in your picture, you should be still seeing, even though not seeing by eyes, but you can still be able to assign something at that point due to existence of the plus Q charge on the left. That existence of something there will generate something that we name electric field in the orange vector right there. You guys with me here kind of, you see what I'm saying here? So my point is, the field is always there no matter what. You don't need another charge, another Q naught, another pair of charge. You don't need anything. The field is already there in your imagination or your visualization or whatever. That's what happened right here. So you already have your electric field due to the charge that generating that field. Okay. And then later, if you decided to place a charge Q naught right here, Q naught, it turns out you can figure out the force F by doing just the products between the charge times the field, and you are pretty much done. Is that good? Yeah, that's how easy it is. See? So what we are trying to say over here is, if you learn how to do the field, getting to the force is simply by taking the charge that you place inside the field, and you are done. So that's why I can give you a conclusion over here. The definition of the field is exactly that. It's the force per unit charge. That's it. So think of it like it's just the G, gravitational acceleration 9.8, the G is just the force per unit mass. If you have M, the amount of mass, how much force you're going to get? Mg. See, it's the same thing.
Okay.
Got that one? All right. So let me write it on the side here. So G is just, think of it, it's like weight over M, because weight is mg. So your G, gravitational acceleration, is just the gravitational field. What we are going to learn here, we're going to learn electric field. They're both using the concept of field. And what kind of concept of field is this? Is the Jedi concept. Yeah.
Okay.
It's the, I don't know, you feel the force of force field or whatever. Yeah. So that's what it is. The same thing as that field in the Star Wars movie. All right, guys. So that's what it is. So even though it sounds like, simple, but it is this simple. The connection between field and force is simply just that. You place a charge inside a field, the amount of force is just the charge times the field. You place a mass inside the gravitational field, the amount of force, which is the weight, is just the mass times the gravitational acceleration, G, mg. Exactly the same, no difference. Now, the only complication that you have to add on top is just, you have two types of charges. You have two types of charge, positive or negative. So let's come back and take a look at what happened if instead of placing a positive charge there, you place a negative charge instead. Look at the one on the right. So when you have that, okay, actually don't look on the right, look on the left here. I think it's easier. So think about this. If I place a negative charge, Q naught instead, same amount, it's the same amount of charge, but it's negative instead of positive. What will happen to it? Take a look at this equation, guys. This equation is a vector equation. So when Q naught is positive, it's just saying that the force and the field will point in the same direction. You guys with me?
Okay.
Yeah. Look at the bottom and the top here. Electric field is pointing in the upwards to your right direction, the orange vector. The blue, the force also points in the same direction if your Q naught is positive. So there will be no more problem at all if you introduce a negatively charged particle there, because your vector equation will take care of everything. Look at this. If this is negative, what it's saying is the force will just have a negative sign in front of the E, which is point in the opposite direction. So what I'm saying over here is, if you place your negatively charged Q naught there, the force will automatically point backward right there due to that negative sign there in the front. Does that
Okay.
make any sense to you guys? Yeah? It's automatic. this equation F equal to Q times E is automatic, just like weight equal to M times G. But we never had negative mass before, so that's why we never had to think about this one. But now, because you have two types of charge, so that's why we have, but I mean, the vector equation serve that purpose already by itself. So you don't have to think of anything extra. Cool. All right. Now, what if instead of having a positive charge Q generating the field, if you would like to talk about, Ajahn, what about if I have a negatively charged instead generating the field? So nothing to worry about. So what you have about what you have here is if you place a positive charge Q naught there, you guys know opposite charge will attract. So you have a force pointing towards the negatively charged on the left. You guys with me so far, yeah? So once again, if I imagine that I'm gonna just get rid of this, forget about this. Well, John, don't worry about this. I don't care about that one. And just looking at what is going on at point P, and point P is down here. So you can imagine that, oh, your negatively charged particle will generate the field as well, but the field will point towards it. Here. Cool. So that's the only agreement that you have to add on top is if you have a positive charge generating the field will point away from the positive charge. If you have a negatively charged particle generating a field, that field will point towards that negative charge particle. Cool. So this complication is just because you have positive and negative charge. We never had these complications before in gravitational discussion there. Okay, so here's the conclusion there. This is the image that you probably can stick in your head. Any positive charge will have field pointing away from it at all time. All the time. Just grab it like this. If you grab this positive charge here, that arrow that try to visualize or try to represent the electric field around it will stick with you. It will just go along with you all the time. On the other hand, if you have a negatively charged particle, the fields will point to it. So this two figure works. All right, so let's test your understanding here. So now I'm going to place a positive charge here. What will happen to it? See, at this point, the electric field already point away from it. Let me mark it as E, right? Yeah. So when I place positive Q naught charge here, you will get a force. Sorry, just right on top of each other. Force equal to Q naught E, and you are done. Cool?
Okay.
And it's a repulsive force, which makes sense. You place a positive Q naught charge near the positive Q charge. The Q naught charge will experience a repulsive force. Now, on the other hand, if you come down here and you place a negative, let's say I put electron there. There you go. Yeah. The electron has a negatively charged. So what you have over here is the electric field at this point still point away from the source. You guys with me so far? Yeah, electric field point outward. It's diverging. Field is diverging out. มันปลิ้นออก no need to clap there. All right. Now you have force acting on this electron in which direction? Okay, force is just the charge times electric field. See, you have a negative sign in the front because electron has a negatively charged on it. So you automatically get the force pointing inward. See, opposite to the direction of the E, which is pointing outward. And automatically that makes sense because once you place electron nearby and positive charge, electron will feel the attractive force. Point towards it. Cool? Sort of get that one? All right. And everything works exactly just like you have a negatively charged generating the field around. If you place a positive charge somewhere here, okay, from F equal to QE, wherever the E is, F will point in the same direction. But because this one is a negatively charged, the field at that point will point towards it. And the force F will point in the same direction there. Okay, so that makes sense. Once again, you put a positive charge Q naught close to a negatively charged particle, that Q naught positive will get an attractive force, pull towards the negative charge. And on the other hand, if I place an electron here, yeah, next to the negatively charged particle, electric field at this point is point towards it. Yeah, that's what we agree. Electric field point towards the negatively charged particle. The force acting on this is just going to be electric charge multiplied by the E. So it's just saying that wherever the E is pointing to, the force will point opposite to it. So in this case, you're going to get the force pointing outward. And that makes perfect sense, because when you have electrons next to the negatively charged particle, electrons will feel the kick. They'll feel the repulsive force. So it's going to get pushed away from it. And that's conclude pretty much the diagram that representing what is going on around positive charge and negative charge particle. All right, just a quick recap. Positive charge generate the field pointing outward. Negative charge will generate field points towards it. Okay, and now if you have more complicated stuff, don't worry. I mean, you can arrange your charge and all this stuff wherever you like, whatever you like. You just have to figure out the net electric fields at the point. So there is a possibility that you get a electric field curve in some direction, blah, blah, blah. You have to imagine, you don't have to imagine not right now, but what you can imagine at this point is, by looking at this, you should be able to tell a little bit about Ajahn. From the look of it, at the A location, it seems pretty intense. The field is kind of intense. But when you go toward your right side, the surface B, for example, is spreading around, the field is kind of diverge out. So it seems like the field should have a kind of weaker, it's kind of weaker, because you can think in terms of the line intensity. It seems like the density of lines doesn't seem so great on the right in relative to on the left. So you can say, oh, this is supposed to be like a high E. Electric field is supposed to be strong on the left, and this is supposed to be like weaker on the right, something like that. Okay, let me put just the magnitude here. Okay, sounds like a good plan here. So there are some relationship in terms of like the line density that links to the magnitude of the field, plus the direction that associated with it will tell you which direction the electric field should point to and in which direction. But now we have a conclusion that for a positive charge, the electric field pointing outward. For a negatively charged, electric field pointing inward. That's the whole key at this point. Okay, cool, guys? All right, now here comes the thing. When you have multiple charges, then you have to find the net electric field for you to be able to figure out what should be the net electric field at one particular point. And if you keep doing that at all points in the space around this system of charges, then you will get some sort of like the electric field lines. You guys with me here? So now it turns out to be aligned to you. So these lines can be referred to as electric field lines. And the electric field lines will give you a clue what will happen around this charge system. For example, on the left, you can see no matter what, electric field is supposed to point out from the positive and point towards the negative, which makes sense. See, electric field point out from the positive and sort of try to convert to the negative one, which makes perfect sense. But how can you get this figure? Well, use the software then. However, for us, what we should be able to do is, let's say if I pick a point, bam, right there, you should be able to figure out what should be the net electric field at that point. If I pick another point, bam, I should be able to pick a net. I should be able to calculate the net electric field at that point. All right. So you don't have to be able to draw the electric field lines, but all you need to know at one particular point, the net electric field is just the vector summation of all those electric fields. Does that make sense?
Okay.
Here you have only single charge generating the field, but if you have more than one charge, generating the field. So you have multiple fields. All you have to do is you just net them, just add them all together and find the vector summation. After the summation, you get the net electric field at that point. So that's what we are going to do today. All right. And now, how can we calculate that? What you have talked about is just like, directions, equations that links between the field and the force. Now I want to be able to calculate the fields now. So let's trace back a little bit here, guys. So it turns out from the experiments, the magnitude of the electric field depends on two main things. First, how big is the charge that's generating the field? The bigger the field should be stronger. That makes sense, right? So it turns out electric field magnitude is directly proportional to the amount of charge that's generating the field. The bigger the field came from, the bigger charge. On the other hand, you have another one is if you stay further away from the charge, the field is going to get weaker and weaker. So at least it's going to be inverse proportion to the distance from the charge generating the field. Except from the experiment, it turns out it's square function. So it's an inverse square relationship to the electric fields. So it turns out the further away from the fields, further away from the charge, the field is diminishing at the R square factor. Okay, so it's an inverse square law, just like what you saw in the gravitational fields. And that's what's the hope of grand unifying theory by physicists there. All right, so the good thing is this is the equation that you have to calculate. It's proportional to the charge generating the field, and it's inversely proportional to the distance from the charge generating the field. And then of course you have to have some constants because you work in an SI system on and on. So introducing a electric constant over, it's not electric constant, it's a Coulomb's constant here. It's the K. All right, for now, what you have here is we'll have a fixed value of the K, but the form of the equation to calculate the field is just this: K Q over R squared. You done.
Okay.
Now the complication comes in there, because you say that electric field is pointing in the radial direction, diverse, right? It's diverse. But no, right? What kind of vector notation that you could use to identify that kind of diverging property of this vector? The answer is annoying dude over here, guys. The R hat. I don't know you like this R hat or not, but it's gonna be here, stay with us all the time. The R hat is just the unit vector pointing in the radial direction. This is so weird. Okay, but for those of you that have done vector calculus a little bit, I think you have seen this R hats before. But for those of you that haven't done any vector calculus at all, this is equivalent to the I hat, J hat, and K hat. Familiar with this? Okay, the I, J, K hat, these are unit vector in the Cartesian coordinates. So that's correspond to the X, Y, and Z direction. So the I hat, no problem. It's a unit vector pointing along the X axis. What about the R hat here? It's a unit vector as well, but it's a pointing in the radial direction. So the only annoying about the radial is it's not a fixed direction vector. The X axis is fixed. If you set X to be horizontal line, so your I hat is going to be always fixed. It's pointing to your right all the time, right? It's a fixed direction vector, but not like R. The R hat is this, guy. This is the weird one, all right? Just annoying a little bit, but I hope like maybe spend time for a couple of lectures, then I think you will be fine. So R hat is this. This is R hat. It's a radial direction. So this is R hat, but this is also R hat right there. This is also R hat. See that? So you are dealing with a coordinate that does not have a fixed orientation. Well, it's a fixed orientation, but it doesn't have the fixed direction. The IJK has a fixed orientation for those XYZ coordinates, but the R is a radial. So this radial direction could be any direction. It's a radial direction. So it's actually, it's not even 360, right? It's like 720. It's like, I don't, well, it's different units. But anyway, the point is like in all directions, anything that points away from the center of the sphere, you can assign the r hat to it. And that's what the r hat is.
Okay.
Okay, so they try to make this equation a vector equation. So that's why they have to place r hat right there, because we already agreed. Electric field point away from a charge that's generating the field. It's radially outward, bam, diverging out, bam. So that's why r hat is there. Cool. All right, so that's what it is. Now, in terms of the actual calculation, all you have to do is just do the summation of those, kq over r squared, and then you just sum all those vectors together and you are going to get the net electric field done. Cool. All right, let's practice, shall we? All right, and by looking at this first exercise, I think things will be clearer. Let's take a look at this. You have 3 equal positive charge Q are at the corner of an equilateral triangle. Side A. What are the magnitude and direction of the electric field at point P up top due to the 2 charges at the base? You see where it goes here? That's not bad. All right, so all you need to do is just figure out the net electric field at point P due to the other 2 charges. We never find the electric field right on the charge. We don't talk about that. So don't worry about it, because some of you will, Ajahn, looking at this equation over here, what happened on the charge itself with r equal to 0? No, we don't talk about that, right? That's is like a singularity point or something, right? We don't care about that one. Yeah. All right. When we say we don't care, doesn't mean there's nothing in it, but it's just that's beyond the scope of this electricity and magnetism stuff. We don't even know that electrons has a size. We assume that there's no size, there's nothing there. There's so that's why it doesn't make sense to pinpoint anything inside the electrons or proton, on and on, something like that. Okay. So how can you do this, guys? First thing first, that Q on top of the triangle, that Q at the top there is inconsequence. Doesn't matter. You can get rid of this. It's not in your picture. You guys with me now? I don't care. Because all I care about is just the electric field at point P due to the other 2 charges at the base. So it doesn't matter there is any charge at point P or not. We don't care. We only care about the field at that point. Cool? All right, now let's talk about the positive Q on the left. It will generate electric field everywhere. Bam, point out, point out, point out, point out. Does that make sense, guys? It's pointing out in all directions, but you only care about what is going on at point P. So that's what I can just get rid of those. And all you care about is just this direction over here, radial direction, and you are generating the vector, electric field vector, pointing away from it. Done. Does that make sense, guys? Very good. All right. Now look on the right, the positive Q on the right. It will do the same thing. Around this, there we have electric field all over the place, everywhere. But we only care about what is going on at point P. So let's do that. Around point P, electric field will point in the radial direction outward. So at point P, you are going to get an electric field pointing away from the charge generating it. Cool? And what you have to figure out is what is going to be the sum of these 2 electric field. Let me call this E on the right, and the other one I can call it E on the left. There you go. Cool. All right, so let's calculate what is the magnitude of the E on the left. See, out now I only can take just the magnitude of it because I already figured out the direction. So all I can say is just the K, Q, same Q over here, yeah, over the distance over here from the charge to the point of calculation is A. So I put A squared there. That's it, I'm done. So I can say it's the K, Q over A squared. And I can put R hat here if I want. Now you can see how it's working now. But the only thing that I need is just, I know the direction already. I only need the magnitude. So the magnitude is just going to be KQ over the distance squared. That's done for the green business over there. Now let's move on to the blue, the electric field on the right. So on the right, the magnitude of the electric field will be just K, the Q that's generating it, that's the Q there, over the distance, the same distance right here, that's just still A. And that's it, that's my magnitude there. So if you want to write this E from the right, the blue one, in terms of the vector, it will look like K Q over A square R hat. See, R hat is everywhere. But it's a different R hat, of course. There's one green, there's one on the red. The center of the whole R hat business, it depends on the charge that's generating the field. Okay. All right. Now, once we have this, so from the symmetry, actually, you can tell right away that the magnitude of the electric field is supposed to be exactly the same. That makes sense, right? Because same distance, same amount of charge and everything. So all you need to figure out is what is the net vector summation here. So what I can do is I can break this vector into two components on the left. And I can do the same thing on the right. I break this into two components here on the right. Cool. All right. And now from symmetry, you can tell right away that the two on the horizontal axis will cancel each other out. You will only have the net upward electric field, which is fine. You can do that. So what I have over here is you're going to have ER. Okay. So now I can use some geometry a little bit here. Because it's an equilateral triangle, I know this is going to be 30 degree. This is going to be 30 degree. So this is going to be my 30 degree. Cool. All right. So that's what you have there. It's the E cosine 30. That's what you have from the blue. And you're going to have E L. Oh, I think I wrote it incorrectly. Guys, sorry. It's E sub R already cosine. My bad. There you go. Cosine 30. Okay. Plus E sub L cosine 30 as well. What else could it be? That's my 30 angle as well. Cool. So the net sigma E will be only pointing upward with the net magnitude of 2KQ over A squared. Okay, you guys agree with me? Because I know what the ER and EL should be. When next time, I don't need to write vector and put the absolute sign in here. I can just write it as EL. Everyone knows without that arrow on top, that is just a scalar quantity. So I can write this one as an ER. Same thing. Just make it easier to write on the paper or on screen there. So your net electric field magnitude is 2KQ over A squared. If I want to rewrite this one as a vector, I can just say, take that magnitude here, and I just say, up. That is fine. All right, for this course, if you would like to just say up, like taking this arrow up, that is fine. But to be a little bit more sophisticated, if you want, you can just say it's like J hat. That will be neat. Okay.
Okay.
All right. But anyway, or you can just write like a sentence saying that it's 2KQ over A squared pointing upward. That is fine. Okay. I'm okay with it. All right. So you got how it's done here. So conclusion over here is at point P, the net electric field is pointing upward with the magnitude of 2KQ over A squared. And I mean, I can just like a spoiler alert here. But Ajahn, if I want to calculate force, can I calculate the force? Because Ajahn just erased the charge that was here before, right? There is a positive charge here, positive charge Q there. So can you calculate the charge acting on the positive charge at the top of this triangle? Ajahn, that's easy. If you want to figure out the force, it's just going to be if this charge is same as the Q, you just take the Q multiplied by the sigma E and you are done. See how simple it is for you to get back the force? Whenever you already sort of like have the information about the field, the force is just a charge times the field at the position of that charge, and you are done. So that's why for this example over here, I can just erase that positive Q charge at the top of the triangle because I don't care if they only care about the field at that point. But if you want to get back to the force, just take that charge, multiply by the field at that point, and you are done. วันนี้โอเคพอรู้เรื่องไหมพอได้ไหม I'll try to go slowly just to make sure that everyone just grab the whole idea of the field. Okay, let's do it one more time. Try this one, guys. Everyone try this. Okay, go ahead. Woo. All right, guys, try this one. I'll give you like a 1 minute head start. Just read the problems and then try to sort of sketch the process or whatever the things that you want to do, you know, in your calculation there. So you have two charged particles placed on an x-axis. Now notice that one is negative, one is positive, and the location is x equal to 3 meters, and the other one is also 3, but on the left. Now find the magnitude and direction of the net electric field produced at point P, which is at 4 meters away from the origin on the y-axis. All right, guys, just give it like a first step for me here. What do you think? Should be quite all right. Yeah. Okay. First thing first, in your head, with all you have to worry about is to make sure that the direction of the field is correct. Now your negative Q charge will generate the field around us, but at the location of the point P. Okay, electric field will be in along the radial direction there, but because it's a negatively charged particle, the electric field will point towards it. Does that make sense? Okay, now turn our attention to the positive Q on the right. The positive Q on the right will have electric field point radially outward in all directions. But at the position P, the the electric field due to this positive charge will point away from it. Cool? Make sense? Now, let me call one more time the green to be E. Let me call E negative because now it's obvious there's one negative and one positive here. Yeah. So let me name this one E positive. Yeah, because it's the vector. Let me put arrow on top for now. Cool. Now let's calculate what is the E positive magnitude, guys, because we already figured out the direction. So all we need is just the magnitude of this vector. So it's going to be K constant, the charge that's generating the field, divided by the distance from the charge to the position of the calculation. Because they said this is 3, this is 4, so we know this is going to be 5. It's a right triangle, so I can put 5 square over here and I'm done. Cool? Okay. And then you try again with the E negative magnitude. It's going to be the K, the Q that's generating the field, divided by, once again, the distance, and it's going to be 5 square as well, and you are done.
Okay.
So you notice something here? When I try to calculate the E negative, I don't have to put negative sign at the position of the Q anymore. You guys with me with this? The reason is because you only care about the magnitude at this point. You already figure out the directions. It's pointing in along the green vector. It's done. So what you have left to calculate is just the magnitude. And when you talk about the magnitude, there's no negative sign, right?
Okay.
It's just magnitude. So that's why it's kind of like you can think of this one as a rule of thumb here in the evaluation of the electric field, right? Of course, you have two things to do, directions and magnitude. The direction, just have to figure out from the figure or whatever, the setup that you have. And the magnitude is from the Coulomb's law, KQ over R squared. But in the process of calculating the magnitude, you don't have to take the negative sign into account anymore because you already figure out the directions. So just grab the numbers and then you'll be done with. Okay, so with this, you're almost done, guys. Just find the net electric field. All right, for those of you that are still familiar with this summation of the vector, just draw this one completeness just for fun. But there's nothing to it now. You want to find the net vector. That would be your sigma E, right? But of course, the way that you actually execute this one is you just break this into two components, just like before, and break the green into two components as well. There. And as usual, the vertical components, from the look of it, by symmetry, they're going to cancel each other. So this one gone along with this. So you only have the net electric field pointing to your left. Okay, how big is that? Well, that's no big deal. Zoom in a little bit here. If you call this theta, I gonna be able to call this theta. Oh, which one should I call? This is theta right there. There you go. All right. So that means one on top. This one is going to be a plus sine theta. And the horizontal component for the green is going to be a minus sine theta as well. I mean, they must be the same, okay? Because this is going to be my theta as well. Cool. So what you get from there is now your net electric field magnitude, right? Just only need the magnitude. Magnitude is going to be E plus sine theta and the E minus sine theta. All right, I just write this one for clarity, but I mean, you know, at the end already, it's going to be twice the E sine theta. Just plus or minus doesn't matter because they have the same magnitude. And it's going to be 2 kq over 5 squared. Sine theta is just opposite over hypotenuse there. So it's going to be 3/5. Okay, and now you just substitute the value into it. Just do it once so you see how to substitute numbers into this one too. Now the K is a constant that's given as approximate value to be 9 times 10 to the 9. Okay, and the unit will be a little bit crazy, but you can put it in the unit of, like, let's say Newton per Coulomb square meter square, on and on, if you like. Right, but don't worry about the unit at this point. Let's just say you know the numbers of the K, you just put it there. The Q is the charge. The charge is 3.2 times 10 to the negative 19. Just plug it in there. That's a Coulomb. And then the rest are just numbers, 3/5, and then you have 25 down here, and then you're done. Cool.
Okay.
Okay, and you want the direction of this one? Well, John, what is the direction? You can say your sigma E is just going to be the magnitude that you just got. You can put negative I hat if you're familiar with that. If you don't like the I hat, just say it's point to the left. Then you will be fine.
Okay.
พอรู้เรื่องไหมเนี่ย? Is that fun? It's kind of like having fun doing some vector calculations here and there. But of course, to get those vectors, you have to use the KQ over R, which is the Coulomb's law. Yeah, pretty much. But I hope by showing you this, it's not that bad anymore to calculate electric field. The only agreements that you have to sort of like agree is positive charge generate the field pointing away from it. Negative charge will generating a field towards it. All right, and now you use this to draw the vector diagram and try to figure out the net vector summations from those electric field generated in your system. Not bad, is it? I think it's quite doable, I guess. All right, okay, let's do last one, guys, for the day. All right, sounds like fun. อันนี้ช้าไปไหมเนี่ย? I'm going too slowly here, but I just want to make sure that I don't left anyone behind. All right, no one's left behind here. Just go slowly. All right, good. All right, cool.
Okay.
All right. In the figure, the 4 particles are fixed in place and have charges Q1, Q2, Q3, Q4 are given. No problems there. Now, this problem is nice in the sense that now we don't have like horizontal per se. It's just sort of like, you know, a little bit oriented a little bit. That's kind of nice. Just, you know, change the mood here. The distance D given to be 5 microns. What is the magnitude of the net electric field at point P due to these particles? All right, guys, give it a shot. Woo. Not bad. All right, so think about this a little bit before I just give you the full solution here. It's kind of good exercise to test your understanding of electric field calculation here. You have Q1, Q2, Q3, Q4, you have distances, you have, you know, everything set up. So the idea is you go one by one and see what happens at point P. So it means at point P, you're going to have 4 vectors come from 4 charges. Does that make sense? Okay, it's got to be there. So let's start from Q1, shall we? So the Q1 and Q2, they are positive charge. So we kind of know that around this positive charge, we'll have electric field points away from it away from it. So Q1, all right, let me just exaggerate a little bit here. So the Q1 will have electric field around this. Yeah, see that I try to draw like a faint line over there. All right, but at point P, the electric field will just have to point in this direction there, radial direction. Cool. At P, you're going to have a vector of the electric field vector coming from Q1 pointing away from it. Done. That's the first one. I can name this one E1, shall we? Okay, let me use the color coded here. E1 vector. And if you want, I can find the magnitude of the E1 right away. It's going to be K, the Q1 over D squared. Cool?
Okay. Okay.
Done? Everyone with me? All right, let's do Q2. The Q2 will have the electric field pointing away from it as well. So at the location of P, the Q2 will generate electric field point away from it. That means you're going to get electric field due to the Q2 pointing away from it. With me, guys? And I'm going to name this one E2 vector. We can calculate the magnitude of the E2 vector by saying that E2 is going to be K, Q over same D squared. But the good thing about this one is, if you notice, they're both sharing the same magnitude of charge, 5e. So I can substitute this 5e, substitute this 5e. E is just the electronic charge, 1.6 times 10 to the negative 19, blah, blah, blah. But the point is, the magnitude of E1 and E2 are exactly the same. Same charge, same distance, but they are pointing in the opposite direction. So at least these two vectors cancel. Isn't that nice?
Okay.
So your job is going to be a lot easier now because I don't think you have to do any like vector components or whatever. It's already gone. Now move on to Q3, shall we? Q3, it's also positive. So that means what you get here is the electric field coming out, right? And let me draw it again. So it's going to point out there, blah, 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 yeah, everywhere. So what we have, just the one that we care about is the one that actually going through point P. And because the Q3 is positive, so it's going to generate electric field pointing in this direction away from the charge, Q3. Cool? Right, is that too small there? Let me do like a big one here. There you go. All right, so it's going to have electric field coming out there. We can figure out the magnitude as well. So the E3 is going to be K, Q3 over, now the distance still D, so it's D squared. So I can put K 3E, I don't have to take in the sign anymore, over D squared. Just leave it there. Now I know the magnitude of the E3. That is my E3, the blue. Now the last one, guys, the Q4. Now the Q4 is negative 12. All right, so the negative 12. So that means the Q4 is negative. So let me draw that line there. Okay, let me change the color here. Let's do like orange there. So the Q4, that will have its own electric field, blah, 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 no problem, everywhere. But because it's a negatively charged particle, electric field will point towards it. Yes, yes, okay, very good. So let's get rid of all those annoying parts. Just left with the one here. At point P, you're going to get the electric field pointing towards it. So let me pick the color to be orange here. There. With me, guys? Okay, Q4 is negatively charged. So electric field at point P will point towards the negatively charged originating the field. So this is my E4. There you go. Vector. And we can find magnitude of the E4. It's just K, Q4 over, now the distance is 2D. The whole thing squared. Cool, not bad. So now substitute in the value. Q4 is 12E. I don't have to take the negative sign in anymore. I know the direction already. Over 4D squared. So let me chop here. I get 3KE over D squared. By accident, if you notice, the magnitude of the E3 and E4 are exactly the same, but they are pointing in the opposite direction. Cool. What does it mean? These two also cancel. So in conclusion, what you have over here is your net electric field at point P is 0, and you are done.
Okay.
Not bad, guys. Okay, that's very doable. All right, so just go back and check it out or try it yourself. Just redo the problems, and if you want to test your understanding one more time, that would be fine. And after you're done with that, I will post exercise in the homework that you have more problems for you to solve, and then sort of like, get yourself used to this business over here. And we're going to have a lot more fun next week dealing with electric fields and electric forces and all the stuff that follow this electricity business. All right, guys. So I think that is it for today. All right. Any questions? All right. If not, then all right, take care of yourself and have a nice holiday. I'm not, it's a holiday, actually. It's a weekend. All right. Have a good weekend, and I'll see you guys next week. Okay. Bye-bye.